Hey everyone and welcome back. In this video we're going to now begin our discussion of continuous random variables and probability functions that are defined on them, often called probability density functions. We're going to describe how we can find probabilities via these PDFs, and also how to calculate the expected value, variance, and also other things such as the median and percentiles of them. As usual, we're going to end this video with a few examples just to test your understanding. Let's get started. Alright, so as usual, we're going to begin with a definition of what a probability density function actually is. So we begin by letting x be a continuous random variable, for example, time, space, length, height, something like that. And let f of x be a function that corresponds to this particular random variable. So keep in mind this capital X corresponds to the random variable, and little x corresponds to a value for which the capital random variable x can take. Now notice there is a little difference between the notation that I'm using here versus probability mass functions for discrete random variables. So in this particular type of structure before, PMFs, when we plug in a value for x, we're going to get a probability out again. It's not going to work that way this time with continuous density functions. So when we plug in a value for x into this function f, we're not going to get a probability, we're just going to get a height. So for probability density functions, we're actually going to have to calculate integrals in order to calculate probabilities, right? So there is a big difference between the two variables and functions on that end. So we say that f is a probability density function, and some people just use PDF for short, sort of like how we did PMF for probability mass functions, for this random variable x if two properties hold. So the very first property that must hold is that this function, capital F of x, must always be non-negative for all values x in the domain of the function f, and the integral from minus infinity to infinity of this function with respect to x must be equal to 1. So as I said before, we're going to be calculating integrals to calculate probabilities. So the integral over the entire domain must be equal to 1. So that's pretty much like the total probability is equal to 1, sort of like we had before. So remember, for PMFs, the two properties that must satisfy was that Px of x must always be between 0 and 1 for all values x in the domain of P, and the sum of all of these values must be equal to 1, right? So those are pretty much the continuous versions of these two properties, right? So if these two properties satisfy that the function is non-negative on its domain and the integral is equal to 1 on its domain, then we say that this function f is a probability density function for the random variable x. So let us look at a particular example here to sort of see how we can test or build a function into a probability density function. So we're going to begin by defining capital F of x. So we're dealing with a random variable x, and we're going to assume it's continuous. And it's going to be equal to k e to the power 2x. Now let's assume that this is going to be true on the continuous interval 1, 2. And let's assume it's going to be 0 otherwise, right? So when I say otherwise, that means x belongs to the interval negative infinity to 1 union 2 to infinity, right? So that's just shorthand for that. All right, so firstly, we know that this function must be positive on its domain. So its domain is 1, 2. Some people call this the support of the function, where it's non-zero there. So this function has to be always positive on this particular interval. We know that exponential functions are always positive as long as x is a real number. So we clearly see that k must be a positive or non-negative number, actually, in order for this to be a probability density function. Now clearly k cannot be equal to 0, else the function is always equal to 0, so the integral under it is impossible to be 1. So therefore we can clearly see that k must be strictly greater than 0 for us to even possibly make this a probability density function, right? So let's figure out what that value k must be in order to make this a PDF. All right, so what I'm going to do, so in order for this to be a PDF, clearly it must be positive, but we need to figure out the value of k to make the area equal to 1, and then we can test just to make sure that that positivity criteria is satisfied. So in order for this to be a PDF, the integral from minus infinity to infinity of this function f must be equal to 1. So we see that the support of this function is 1, 2, so that means this is just equivalent to writing the integral from 1 to 2 of k e to the 2x dx, right? And we know that this must be equal to 1. So we need to solve this equation for k, and that should say 1, not 0. All right. So we clearly see that this is going to be equal to k times the integral from 1 to 2 of e to the 2x dx, right? And we know that the integral of e to the 2x is going to be equal to 1 half e to the 2x, and then we need to evaluate this as x goes to 2 and as x goes to 1. So that's going to be equal to what? So that's going to be equal to k divided by 2, e to the power of 4 minus e to the power of 2. And we know that this must be equal to 1. So we clearly see that the only value of k that makes this true must be equal to the number, what is that going to be? That's going to be 2 divided by e to the power of 4 minus e squared. And if you do a decimal approximation for this, you can find that that's going to be approximately equal to 0.0424. So remember that our function was k e to the 2x, right? So that's the function on the interval 1, 2. And we know that if k is a positive number, that means this function is going to be positive on that interval. And clearly this value of k is a positive number, therefore this is a probability density function. So that means if we define f of x is equal to, so we can rewrite this as 2 over e to the 4 minus e squared times e to the 2x for x belonging to the interval 1, 2, and 0 otherwise, then f is a probability density function for the continuous random variable x. Right? So once you have a probability density function for a continuous random variable x, how can we calculate probabilities? So I'm just going to be calling this function f of x, since that's pretty much what we're going to be interested in. So let us see how we can calculate some probabilities. So the first example, suppose somebody asks, what is the probability that x takes a value larger than 1.2? Right? So from the continuous spectrum, that's the same as the integral from 1.2 to infinity of our probability density function. So remember that the support of this function is 1, 2. So from 2 to infinity, this function is equal to 0. That means this integral is equal to the integral from 1 to 2 of f of x dx. So on 1.2 to 2, the function is of course equal to that function that we built, in particular 2 divided by e4 minus e2. So e4 minus e squared multiplied by e to the 2x dx. So you would have to evaluate that integral, which is of course not that hard. And once you actually go through those processes, you're going to find this is going to be 0.9230. Right? So there's a 92 approximately percent chance that x is larger than 1.2. Keep in mind, notice that I did not have an equal sign there, like greater than or equal to. The probabilities are actually the same in the continuous spectrum, and I'll leave to you to sort of think why that is the possible case. But keep in mind, just because it says greater than 1.2, do not start the integral at something like 1.3 or 2 or something, because there's definitely an infinite interval, or a dense interval, some people say, that you're going to be missing for the probability, okay? So let us just look at one other basic example of probabilities. So if I say what is the probability that x is less than or equal to 1.1, so from the general probability perspective, that's going to be the integral from minus infinity to 1.1 of our density function. But remember that the support of this function is 1 to 2. That means from negative infinity to 1, this function is equal to 0. So that means this integral is just going to be equal to the integral from 1 to 1.1 of that value. Remember, e to the 4 minus e squared times e to the 2x dx. And then you go through the normal integration process for that, and you're going to find that that area is going to be approximately equal to 0.0347. So there's approximately a 3.5% chance that x is less than or equal to 1.1. So this is just some of the basics associated to probability density functions. Now let us talk about how we can find the expected value, variance, and other percentiles for this particular distribution. All right, so let us consider the same exact probability density function that we had before. In particular, k e to the 2x on 1 to 2 and 0 otherwise. So we already found and verified that the value of k is equal to 2 over e to the fourth minus e squared will make this function f a probability density function on the random variable x. Now let us see if we can find the median of that particular random variable. So what do we mean by a median of a continuous random variable? So that means the integral from minus infinity to some number m of this function f of x dx must be equal to the integral from m to infinity of f of x dx. And remember, median represents the middle, so half of the data is to the left and half of the data is to the right. So that means this must be equal to 1/2. So you have a couple equations that you can work with. You can either work with this one or you can work with that one, right? So you can either solve the equation negative infinity to m or m to infinity, set that equal to 1/2, and solve that equation for m. So m will be called the median for the random variable x, all right? So let us look at that particular function that we had, and let us see if we can find the actual analytical value. So we're not going to be using any approximations, at least for the start of that, right? So let's assume we want to, let's solve from the left-hand side, right? So let us solve the equation minus infinity to m of the density function, okay? So that's going to be equal to the integral for, so remember from minus infinity to 1 it's 0, so that's going to be equal to the integral from 1 to m. I'm just going to use k, so I don't want that ugly number there, right? So I want to solve this equation for m, right? So we're solving for that upper bound, so we're trying to figure out what value m makes this equation true, okay? So notice that that's going to be equal to k over 2 times e to the 2x, and then we're going to evaluate this at m, evaluate this at 1, and then solve that equation for 1/2. So once we do that, we're going to have k over 2 times e to the 2m minus e squared. That's going to be equal to 1/2. We're going to multiply both sides by 2, so that actually turns out pretty nice. So we're going to have, what is that going to give us? So multiply both sides by 2, that turns that into 1, and then we're going to divide both sides by k. So we have e to the 2m minus e squared is going to be equal to 1 over m. Let's add e squared to both sides of the equation. So e to the 2m is equal to 1 over m plus e squared. And then I'm going to take the natural log of both sides of this equation, and then I'm going to divide by 2. All right. So once I have that, that means m is going to be equal to 1/2 times the natural log of 1/2 plus e squared. And some people may write this as the natural log of the square root of 1/2 plus e squared. Those are, of course, the same exact things. Where's my k? I lost my k, right? Yeah, that m should be equal to a k, right? Where'd you go? How'd he turn into that letter? We don't know, right? So that's dangerous. Don't make simple mistakes like that. All right. So that is the analytical value. So remember, k was equal to 2 over e4 minus e squared. So that's going to be equal to, if we actually plug that in, that's going to be equal to the natural log of the square root of e4 minus e squared all over 2 plus e squared. But that's a pretty useless value, especially for practical purposes. So once you actually evaluate that, you're going to get approximately equal to 1.7169, right? So that will be the median of this particular random variable. So how can we find the mean or the variance or the standard deviation of these things, right? So the formulas are actually extremely comparable to the discrete case. Let's just go ahead and define them. So the mean, or the expected value of a continuous random variable, is going to be defined to be equal to the integral from minus infinity to infinity of x times our probability density function, right? So it's very similar to our discrete case where we sum xpx's. So now we're integrating xfx's, right? Similarly, we have the second moment of a random variable that's going to be equal to the integral from minus infinity to infinity of x squared times our probability density function. So these are the only two basic definitions you need to know. Of course, you could do the third or fourth moment or whatever you want. But how can we find the variance? So remember that the variance of a particular random variable x, sometimes we write that as sigma x squared, that's always just going to be equal to the second moment minus the mean squared. So this formula still holds for continuous and also discrete random variables, so we can still find the first moment, find the second moment, and then find the variance just like we did before. All right, so if we actually go through the process for this particular example, and I'm not going to go through uh, the calculations or whatever. So for example, if we do this same example, so x belonging to the interval 1, 2, and 0 otherwise, you can find for a random variable x that the mean, which is going to be equal to the integral from 1 to 2 of kxe to the 2x dx. So you could probably do some integration by parts there if you want to do that by hand. But once you actually go through that process, you're going to get that's approximately equal to 1.6565. For our second moment, that's going to be equal to the integral from 1 to 2 of kx squared e to the 2x dx. So you could probably use integration by parts 2 times for that if you want to do that by hand, but you can find that's going to be approximately equal to 2.8130. So if you can find your expected value in your second moment, then you can find that the variance is going to be approximately equal to 0.06898. And remember, the variance is never negative. And then we can find our standard deviation for our random variable x, which is, of course, the square root of that number approximately. And that's going to be approximately equal to 0.2626. And always remember, if you have a number that's between 0 and 1, its square root is always going to be larger than that number, right? So a little bit counterintuitive compared to, say, numbers bigger than 1, all right? So that would be the expected value and the variance and also the median of random variables. But what if you want other percentiles, like the 30th percentile, for example, right? So let's find the 30th percentile for x, right? So remember, for the median, we set that equal to a half, which is just the 50th percentile, right? So we're just going to replace the 50% with a 30%, and we're going to get the same exact thing. So our goal is to solve the equation, the integral from minus infinity, I'm going to call it p30 of fx of x dx, and we want to set this equal to 0.30. Right? Now, of course, you could go through the same exact process and solve this equation for p30, but you can actually solve this very quickly in a graphical way, right? So keep in mind that this is just an unknown variable, right, that we're solving for. So what I'm going to do is I'm actually going to subtract both sides by 0.30. So I'm going to have the integral from minus infinity to p30 of xf of x dx minus 0.30, and I'm going to call this a new function of that variable that I do not know, right? So what I want to do is I want to find a value p30 such that this value is equal to 0, right? Now, if you think back to pre-calculus, that is precisely the value of an x-intercept, right? So what I can do is I can graph this particular integral equation, or whatever you want to call it, and you should see that this graph should, and remember our support is 1 to 2, so you should get a number between 1 and 2. So actually, when you graph this particular function, you're going to get something like this, right? So this is the graph of f, capital F, and this is going to be x, and this is going to be capital F of x, right? So this point here, that's going to be p30, right? So you can actually go through the process and find that p30 is approximately equal to 1.5352. Graphical way is definitely the most easiest way to find them, at least pretty quickly, or you can do it by hand if that more is your preference. So those are just the basics of probability density functions, what they are, how to verify them, how to find the first, second, and second moments, variance, standard deviation, median, and pretty much any percentile that you want. Definitely there's a lot of things that we can do with these, and we're also going to give a few examples of special probability density functions in the upcoming lectures. See you then.